In the previous example, we derived the model of a translational system. In this example, in the second example here, let's take a look on the rotational system. So I have a rotational system. Now we are trying to derive the mathematical model of it. So in this slide, as you can see, there are two disks indicated by J1 and J2. So J1 is the moment of inertia of the first disk, J2 is the moment of inertia of the second disk. These two disks are interconnected to each other through a flexible shaft with a spring constant, rotational spring constant of K naught. And J1 is supported to the ground by another flexible shaft with a spring constant of K1, while J2 is supported to the ground through a flexible shaft of K2. Now imagine if I apply an input torque to J1 to the first disk here. I give a input torque of tau x to J1. What will happen to this? Of course, intuitively, both J1 and J2 will be displaced rotationally in angular coordinate independently. So let's say J1 is rotating in a clockwise direction by θ1 and J2 is rotating also in a clockwise direction by θ2. Please take note again on this direction convention, similar to the live demo that you have seen in the previous few slides. Okay, so in this case, we can consider the applied torque tau x as an input to the system, and θ1 and θ2 are the displacement output of the system. Again, θ1 is the rotation of J1 and θ2 is the rotation of J2. Now we are going to derive the model that correlate θ1 to the input tau x and also θ2 to the input of tau x. Same like before, same like in the previous example, we have to analyze each of the element individually. So let's take a look on the first shaft, the shaft in the left side there, the shaft K1. So imagine if J1, because of the input torque tau x, J1 is rotating in the clockwise direction. What will happen? The right end of shaft K1 will also rotate in a clockwise direction by θ1, right? Because the right end of K1 is connected to this J1. Now imagine you have a shaft, the right end, you have a shaft, the right end is twisted to the clockwise direction by θ1. What does it mean? This means you are applying a torque to this shaft in the direction as follows. Because the shaft is flexible, so the torque that you apply to this shaft is proportional to the relative angular displacement of the shaft. So the torque will be proportional to θ1. Imagine you have a shaft, you fix the left end and then you try to twist the right end. So basically you are applying the torque, as you can see, as I indicated with the blue arrows there. Okay, so I draw it again in the slide, as you can see in the middle figure in this slide. So tau 1 here is the torque applied to the shaft. And as I mentioned before, the applied torque is proportional to the relative angular deformation of the shaft, theta 1. So tau 1 is equal to K1 times theta 1, where K1 is the spring constant of the shaft K1. So we have already analyzed the first element, spring K1. Now we can move to the next element. Let's take a look on shaft K2 now. Based on our initial assumption, J2 is rotating in a clockwise direction, right? With the rotation of theta 2. So imagine, because the shaft K2 is the left end of the shaft K2 is connected to the disc J2. When J2 is rotating in a clockwise direction by theta 2, and then the left end of K2, the left end of the shaft K2, will also be twisted by theta 2 in a clockwise direction. Same like our analysis before for the shaft K1, if you keep the right end of this shaft, the shaft K2, if you keep the right end fixed and you try to twist the left end of this shaft, so basically you are applying a torque in this direction. The internal torque applied to shaft K2 is tau 2. Let's call it tau 2, and tau 2 is proportional to the relative angular deformation of the shaft K2, which is theta 2. So in here, we conclude that tau 2, which is the applied torque to shaft K2, is equal to K2 times theta 2. So this is our analysis for the second element. Let's move to the next element now. Okay, now let's take a look on the middle shaft, shaft K0, where the left end is connected to the disc J1 and the right end is connected to the disc J2. As we assume, J1 is rotating in the clockwise direction by theta 1 and J2 is rotating in the clockwise direction by theta 2. Now let's take a look on the middle shaft, the shaft K0. So the left end of this shaft is connected to J1, the right end is connected to J2. J1 is rotating to the clockwise direction by theta 1, J2 is theta is moving to the clockwise direction as well by theta 2. So how to derive the torque applied to the shaft? Same like in the previous example, when we were talking about translational system, we need an assumption in here, because the direction of the torque will depend on theta 1 and theta 2. So for simplicity here, let's take an assumption that theta 2 is greater than theta 1. Imagine now you have a shaft, flexible shaft, and then you try to twist the right end more than the left end. What do you feel? You will have a notion that you are applying a torque in this direction. So you twist it in this direction. Imagine you have a shaft. You rotate this more than in this side. So basically, if you have this case, of course, you are applying torque in this direction. You twist it like that. And the applied torque, obviously, is proportional to the relative angular deformation. Since we have assumed theta 2 is greater than theta 1, so the applied torque tau 0 is also proportional to theta 2 minus theta 1. with the proportion of the spring constant K0. Okay, so we have already derived the torque applied in the third shaft. Now we can move to analyze the disc individually. Okay, in the previous few slides, we have already derived all of the torques acting on each of the shaft K1, K0, and K2. Let me redraw again all of the analyzed torques in all of these three shafts. I put them all together with the two discs with inertial J1 and J2 in these slides. So we have already analyzed the torques applied on shaft K1 from the slide 28, the torques on K0 as well as the torques on K2. Now let's take a look in particular first on the disc J1. If you see the system here, the right end of shaft K1 is connected to this J1, right? And then there is a torque tau 1 acting on the right end of shaft K1. Of course, this torque will be transferred to the disc J1, and there will be a reaction torque acting to this J1. The reaction torque is a reaction to the torque tau 1 in shaft K1. But of course, the direction of the torque will be on the opposite direction. So after I transfer the torque tau 1 to this J1, I will have this following torque. Right? The same thing also happened to the torque tau 0. The torque tau 0 that is coming from shaft K0. The left end of torque, shaft K0, we have a torque tau 0, and this will be transferred to this J1 with a reaction torque in the opposite direction with the same torque tau 0. This one, right? So we have already completed transferring all of the torques from shaft K1 and shaft K0 to the disc J1. Now I will do the same thing to this J2. The left end of shaft K2, we have a action torque of tau 2. This will also be transferred to this J2, but of course the reaction torque will be in the opposite direction. Same thing also to the torque tau 0 in a shaft K0. This will also be transferred to this J2. If we transfer these two torques, this is what we will have. If you observe it, the reaction torque tau 0 in this J2 is the opposite of the torque tau 0 in shaft K0. Same thing to the torque tau 2. So after we complete all of these things, we can start to analyze the disc one by one. I started with the first disc, the disc with inertia J1. So this is the same drawing for disc J1. If you refer to the problem of this example, you see there is an input torque which is equal to tau x that is applied to this J1. And there are two reaction torques from shaft K1 and K0 that are also acting on the disc, which are tau 1 and tau 0. This disc is rotating in a clockwise direction. So technically, there will be inertial torque rotating also in a clockwise direction, where the inertial torque is equal to J1 times the acceleration of the disc, theta 1 double dot. Referring to the Newton's second law, Newton's second law says the total torque acting on a disc will be equal to the inertial torque. Again, the inertial torque here is J1 times theta 1 double dot. So I just sum all of the torques acting on the disk. Tau 1 is acting in the counterclockwise direction, tau x in clockwise direction, as well as tau naught. Clockwise direction is the same direction with the inertial torque J1 theta 1 double dot. So I can derive this equation. Negative tau 1 because it is rotating in a counterclockwise direction, plus tau naught in clockwise direction, plus tau x in clockwise direction as well, will be equal to J1 theta 1 double dot, which is also in clockwise direction. We have already derived all of these torques in the previous few slides. We have already derived what is tau 1, what is tau 2. You can refer again to slide 28. So I can rewrite this equation into this form. Of course, you will get this after you rearrange the mathematical equation. So you will have the equation that correlate the input tau x to the output of this J1 and this J2, which are theta 1 and theta 2. So up to this point, we already obtained the first equation with regards to this J1. Now, let's move to the second disk, this J2. We will analyze this and then we will apply the Newton's second law. So here I redraw the schematic diagram of J2. There are two reaction torques applied to this J2 disk. Tau naught from shaft K0 and tau 2 from shaft K2. And from the problem, we know that we have already assumed at the beginning that J2 is rotating in the clockwise direction with a motion of theta 2. So what does it mean? It means there will be an inertial torque rotating at the same direction in a clockwise direction, and the inertial torque will be equal to J2 times theta 2 double dot. Moving forward, then we can apply the Newton's second law. The torques applied to J2 are tau naught and tau 2, but both of them are pointing towards clockwise direction, counterclockwise direction. So in this case, then I can derive the equation that negative tau naught minus tau 2, because both of them are in the counterclockwise direction, will be equal to J2 theta 2 double dot, which is pointing to the clockwise direction. We have already derived tau naught and tau 2 in the previous few slides, so I will just substitute the value of tau naught and tau 2 in this equation. After rearranging the mathematical equation, I will get this differential equation as the second equation to the problem. In this slide, I rewrite again the two equations derived from this J1 and this J2. So if you look to these two equations carefully, these two equations will relate the input torque tau x to the output of theta 1 and theta 2. You have two outputs, theta 1 and theta 2, which means you have two unknowns here. If you know the input torque tau x, you can solve theta 1 and theta 2 accordingly. How to do that? Of course, you need help from Laplace transformation. Okay, in these slides, you can see the same equations, but after I transform it to Laplace domain. So the first equation, equation 3, is coming from the Laplace of equation 1, and equation 4, of course, is from equation 2. So if we know, let's assume if we know the initial condition, theta 1 when time is equal to 0, theta 2 when time is equal to 0, as well as for theta 1 dot and theta 2 dot, we can evaluate the value of theta 1 and theta 2 accordingly if you know the input tau x. So this is how we solve the problem of a rotational system using Laplace transform. In this slide, I will share you on the guideline of how to derive a mathematical model of mass spring damper systems. So as what we have already discussed in the last two examples, you have to start it defining the direction, which one is positive, which one is negative. After that, you need to define the direction from the equilibrium position for each inertial element, whether it is mass for translational system or inertial for rotational system. And then the next step, you have to assume the relative displacement across every spring and damper element. This will help you to define in which direction the action force or the action torques are acting on the spring or on the damper elements by defining whether the elements are in a compression or in a stretching stage. The next step, you can determine the direction of the forces on the spring and the damper elements. And then you need to transfer all of these forces or torques to the inertial element, where the transverse force or torque will have the opposite direction. This is because of the action-reaction law. After you transfer all of the forces and the torques applied on these elements, on the spring and dampers, to the inertial element, you can start to apply the Newton's second law. From there, you can start to derive the equation of motion in terms of differential equation. If you need to analyze it further to have the solution, of course, you need to use the Laplace transform to transform your differential equation problem to algebraic equation, and then you can solve to get the final solution. Let's call it recipe to derive the model of mass spring damper systems. Okay, as a summary, what we have discussed in this third session, we have discussed few dynamic model of mechanical systems. Thank you for your attention, and we will see again in the next session.